everyone, welcome to the next session of Finite Element Analysis. In this session, we are going to talk about another numerical method which is used. It is called as finite difference method. Let's get started. All differential equations cannot be solved by exact mathematical methods, which means the method of finding complementary function and particular integral, which I have discussed in the previous session. In such cases, the differential equations are solved by numerical methods. Finite difference method, that is FDM, is one of the numerical methods to solve a differential equation. FDM involves use of Taylor series of expression of a function. You are well versed with the Taylor series method in mathematics, which is written as f double dash x is equal to f of x plus h minus 2f of x plus f of x minus h upon h square. This is nothing but the expansion of f of x plus h and f of x minus h, and when you add both of them you get this equation. Similarly, f dash x is equal to f of x plus h minus f of x upon h, or it can be written as f of x minus f of x minus h upon h. So these equations you have already seen in mathematics. These are equations from Taylor series method. When I modify these equations, I can write the equations for finite difference method, that is yi double dash. Here you can see it is fx double dash, it is written as yi double dash. Here I means the number of iterations that I am going to perform. Iterations means trial and error method, you must have seen. So I can have I is equal to 1, I is equal to 2, I is equal to 3. You will have few iterations and you will be getting the solution. So from here I wrote f double dash x as yi double dash. This term is yi plus 1 minus 2yi plus yi minus 1 upon h square. This is one equation. This is in line with these equations. And the other equation is, instead of f dash x, I have yi dash is equal to yi plus 1 minus yi upon h, or yi minus yi minus 1 upon h. So these are some equations for finite difference method. I'll give you an example. D square y by dx square minus y plus x square is equal to k. This is just an equation. K is a constant value. The domain for this independent variable is a to b. This is a closed interval. I hope you are aware of the interval types. One is, say, 0 less than x less than 1. This is an open interval at both the ends. If you have 0 less than equal to x less than 1, this is an open interval, or it is closed at one end, open at the other end. You have 0 less than x less than 1. Again, this is your semi-open interval, and you can have a closed interval like this, which is 0 less than equal to x less than 1. So these are the four types of intervals that is possible. Now y at a is p. This is one of the boundary condition. Y at b is equal to q. This is another boundary condition. Now let me assume that the solution of this differential equation is f of x. Now f of x means it's a function of x, so it can be any equation. Let me say that this equation which I have written, if I plot some values, for example, if I take certain values of x, I'll get some value of y. Say at x0, the value is y0, at x1, value is y1, and similarly up to x4. So when I join these points, say I get a curve. Now these divisions are equal, that is h, as you observe. This h is b minus a upon n. Now n means dividing the interval a to b. As we saw that x has a domain from a to b. You can see the diagram also, from a to b. So I am dividing, let's say, into 4 divisions. You can divide into n number, that's your choice, but I have divided into 4. So this is b minus a upon n, that is 4. Here you can observe from the diagram, x0 is a. So y0 at this point from the given equation is p. Similarly at x4 the value is b and y4 will be q. So that's what I have written over here. And if you observe in this diagram, x1 is x0 plus h, which is x0 is a, so a plus h. x2 will be a plus h, so this becomes a plus 2h. x3 will be a plus 3h and x4 will be a plus 4h. So this is how this equation has been written. Similarly for y1, which will be at x1, if you see the diagram, y1 is calculated over x1. At this point, we can say y has to be in terms of x0 plus h. Now, why I am writing x0? Because if you observe here, this a is also equal to x0. So, instead of writing a plus h, I have written x0 plus h. Same way for y2, which is y at x equal to 2, it can be written as a plus 2h, or it can be written as a plus h plus h. A plus h is x1, so x1 plus h. y3 is y at x equal to 3, so this y is x2 plus h. And lastly, y4 will be y at x4, which is y at b is equal to q, which I have told you before. Now, yi is going to be y in terms of xi. It is just a linear algebraic equation which you can write. Similarly, if you want to write yi plus 1, again you can write a linear algebraic equation. Now, when I say y is xi, I can say it as 3xi cube plus 4xi square plus 2. This is an equation for yi. Suppose if I write in terms of I plus 1 here. That's it. So this is the very simple meaning of y is a function of x. That's what you can go round and round, write these equations. When you substitute in these equations, you will get a equation which will be this equation y is equal to f of x. Once you get this equation, you substitute over here, you should get the solution. Or rather, I would say by using finite difference method, you can assume a solution and prove that it is a solution for this equation. So you can go either way. So this is all about finite difference method. In the next session, we will start with the numericals so that your idea about these concepts become much more clearer. See you in the next session. Thank you.